All right, today we're going to pull back the curtain on the invisible forces that basically run the world of organic chemistry. We're talking about the forces that decide if something is a gas, a liquid, or a solid. Let's dive in and see how it all works.
So let's kick things off with a little puzzle. You've got methane and you've got water. Both are pretty small molecules, right? But look at their boiling points. They are worlds apart. One's a gas way, way below freezing. The other is a liquid we use every day. So what's the deal? What's the secret? Well, there's a really cool principle at play here, and we're about to crack it.
And the answer is intermolecular forces. You can call them IMFs for short. The best way to think about them is like an invisible glue that holds molecules together. It's this stickiness that dictates physical properties like boiling points. It makes sense, right? The stronger the glue, the more energy you have to pump in to pull the molecules apart and turn them into a gas.
Okay, so not all of this molecular glue is created equal. Let's put these forces into a power ranking. We're going to start with the weakest contender and work our way up to the undisputed heavyweight champion of intermolecular attractions. First up, we have London dispersion forces. Now, the most important thing to know about these is that they're universal. Every single molecule has them, no exceptions. They happen because electrons are constantly zipping around. Just by chance, you might get more electrons on one side of a molecule than the other for a split second. That creates a tiny temporary magnet, a dipole, that can attract another molecule nearby. It's a very fleeting, weak attraction.
So when you look at really simple nonpolar molecules, like the alkanes here, your methanes and propanes, this is all they've got. London dispersion forces are the only tool in their toolbox for sticking together. They don't have any other tricks up their sleeve.
And because of that, in our power rankings, yeah, they're right at the bottom. These are by far the weakest of the intermolecular forces.
Okay, moving up the ladder, we get to dipole-dipole interactions. Now, unlike those temporary forces we just talked about, these happen in what we call polar molecules. These molecules have a permanent positive end and a permanent negative end. You can pretty much think of them as tiny little bar magnets.
Haloalkanes are a fantastic example of this. You've got a halogen, like chlorine, which is way more electronegative than carbon. That means it's constantly hogging the electrons in their bond, creating a permanent negative charge on its end and a positive charge on the carbon's end. So these little molecular magnets can line up positive end to negative end, creating a much more stable, stronger attraction.
This permanent attraction means that dipole-dipole interactions land squarely in the middle of our power rankings. They're a pretty significant step up in strength from the London dispersion forces.
And now, for the main event, the top tier, hydrogen bonding. Now listen, this isn't a totally new kind of force. It's really just a supercharged, elite version of a dipole-dipole interaction. But the rules for it are very, very specific. It only happens when you have a hydrogen atom that's directly bonded to one of three things: nitrogen, oxygen, or fluorine. That's it. N, O, or F. Check out these alcohols. See that? In every one, you've got a hydrogen atom literally stuck right onto an oxygen atom. Because oxygen is so electronegative, it creates an incredibly strong partial positive charge on that hydrogen. This allows for an exceptionally powerful attraction between molecules. And by the way, this is the secret to water's ridiculously high boiling point. So at the very top of our power rankings, without a doubt, is hydrogen bonding. It's the strongest intermolecular force we're going to cover. And trust me, it has a massive impact on the properties of any molecule that can do it.
Okay, so we know the forces now, but how do you actually use this knowledge, say, when you're staring down a question on an exam? Let's break down a simple chemist's 5-step playbook for comparing any two molecules.
Here it is. It's a really logical flow. First, just identify the compounds you're working with. Second, explain the specific forces that are present in each one. Third, you'll talk about why one force might be stronger than the other. Is it because of the type of force, or maybe the size of the molecule? Fourth, you connect that force strength to a physical property, like its boiling point. And finally, you wrap it all up with a clear conclusion.
Let's put this playbook into action right now. Methane versus butane. Step 1. Got 'em. Step 2. Both are nonpolar alkanes, so they only have London dispersion forces. Step 3. Okay, but butane is a much bigger molecule with way more electrons, which means its temporary dipoles are stronger and more frequent. Steps 4 and 5, therefore, butane has stronger IMFs, and that's why it has a higher boiling point. See? Simple as that.
All right, let's zoom out for a second and see how these forces really play out across different families of organic molecules. These are called homologous series, and this is where it all clicks into place. This table just lays it all out perfectly. You can see the progression so clearly. We start at the bottom with alkanes, with only those weak London dispersion forces. Then we level up to haloalkanes and their moderate dipole-dipole forces. Alcohols come in strong with hydrogen bonding, and right at the top you have carboxylic acids, which are the strongest of all because they can actually form 2 hydrogen bonds at once with another molecule. It's just a beautiful, clear progression of increasing strength.
And this visual just drives the point home, doesn't it? On one side, you've got simple alkanes with their kind of weak, fleeting attractions. On the other side, you've got carboxylic acids forming these incredibly powerful networks of hydrogen bonds. The big takeaway here is that a molecule's specific arrangement of atoms, its functional group, is what determines the dominant force, and that force dictates pretty much all of its physical properties.
So there you have it, the power rankings of the forces that hold molecules together. You now know the secret handshake of chemistry. So the question I'll leave you with is this: where else in your daily life can you spot this stuff happening? I mean, think about why oil and water don't mix, or why rubbing alcohol feels so cold when it evaporates off your skin. The answer is right there, in these incredible invisible forces.